What would your eyes actually see if you pushed a spaceship closer and closer to the speed of light? Not what sci-fi movies show you, not a simple blur of stars or a dramatic warp effect. The real answer is far stranger, more beautiful, and more unsettling because it forces us to face how light, time, and space truly behave. So let's take this journey together. Imagine we're aboard a spacecraft leaving Earth, accelerating continuously, faster and faster, with no limit on how long we can keep the engines firing. As we lift off, the ship begins at rest, and then the thrust builds. You'd expect that rising speed would become unbearable for the human body, but speed itself doesn't affect you. If two trains pass each other smoothly, you can't feel which one is moving. In the same way, inside the spaceship, you don't feel the speed, only the acceleration, the push of the engines pressing you into your seat. As long as that push stays reasonable, the ride remains comfortable, even as we reach extreme velocities. But high speed brings a hidden danger: collisions. At these velocities, even a tiny speck of dust would hit with terrifying force. A grain of sand could cause catastrophic damage. So in our thought experiment, the ship is equipped with a protective force field, something that repels dangerous particles and clears our path. With that protection, we're free to accelerate deeper into space. And as we do, the first strange effect appears. The sky begins to change shape. The stars ahead of us seem to shift, not because they move, but because our motion changes the direction their light appears to come from. This is called the aberration of light. To picture it, think of driving fast in the rain. The rain falls straight down, but through your windshield, it looks like it's coming toward you from the front. The faster you drive, the more the rain seems angled. In the same way, as we accelerate, starlight that originally arrived from all directions appears to tilt forward. The entire star field compresses into the direction we're traveling. This compression isn't subtle. Ahead of us, the sky contracts into a tighter and tighter region, and as more light gets focused forward, it also grows brighter. Meanwhile, behind us, the opposite happens. The sky stretches outward and fades. The rear becomes darker, emptier, as fewer and fewer light rays can catch up. And this bending of what we see doesn't just shift star positions, it warps the shape of everything. Imagine the universe as a vast grid, a structure of straight lines stretching through space. Normally, perspective makes those lines converge in front of us, but as our speed increases, aberration distorts the entire view. The grid seems to squeeze forward, and lines that should look straight begin to curve and bend around our vision. Even solid objects don't look quite right. If we passed something at high speed, it would appear strangely angled toward us. This is known as the Terrell-Penrose rotation. Instead of seeing objects simply squashed, we see them visually rotated because light from different parts of the object reaches us at different times. And then another effect enters the scene: the Doppler effect. You've heard it with sound. A siren's pitch changes as it moves toward or away from you. Light behaves similarly. When we look back toward Earth as we speed away, Earth's light takes longer to reach us. If we could zoom in with a telescope, we would see people and events moving in slow motion. Each tick of a clock on Earth arrives more stretched out than the last. The image dims and Earth shifts toward red. But ahead of us, it's the reverse. We chase light, catching up to it. Stars brighten and shift toward blue, and their clocks appear to tick faster. At this stage, though, these are still optical effects, distortions caused by how moving observers receive light. If we turned around now, nothing fundamental would have changed. But after hundreds of days of relentless acceleration, we begin to approach the ultimate limit, and that's when the illusions end. That's when the illusions end, because at near light speed, special relativity stops being a visual trick and becomes a physical reality with consequences you can't undo. The first major change is time dilation. To understand it, picture the universe as a four-dimensional fabric called spacetime, 3 dimensions of space and 1 dimension of time. Everything, Earth, the stars, and our ship, moves through this fabric along a path. Before launch, our path through spacetime matched Earth's. We were traveling into the future together. But as we accelerate faster and faster away from the planet, our path tilts. Our time direction no longer aligns with Earth's time direction. That's the key. Time isn't a universal river flowing the same way for everyone. It depends on motion. And if we turned around and returned to Earth after accelerating for a long time, our clocks would disagree with the clocks of the people we left behind. We would have experienced less time. We would have aged less. Not because time was slower in some mystical sense, but because our trajectory through space-time was different. Then comes another consequence: length contraction. At speeds close to light, objects contract along the direction of motion. But from our perspective, it isn't just our ship that changes, it's the entire universe. If we're racing away from Earth, then from our frame of reference, the universe is moving backward past us. And as it moves, distances in the direction of travel shrink. That means the space between us and a faraway destination becomes physically shorter in our frame. This isn't an illusion like aberration or Doppler shift. This is a real, measurable effect of relativity. And it leads to one of the most mind-bending truths. With enough speed, you can cross enormous distances in surprisingly little time, at least for you. This is where a common misconception collapses. People often think that traveling to a star thousands of light years away would require thousands of years no matter what, but relativity says otherwise. If our ship travels extremely close to light speed, the distance to that distant star contracts from our point of view. The trip could take years, months, or even seconds for us, depending on how close to light speed we get. In the extreme limit, moving almost at the speed of light, the journey can feel nearly instantaneous. But there's a catch. While we experience very little time, the people on Earth experience a lot. For them, thousands of years pass. So yes, in principle, you can travel across the galaxy within a human lifetime aboard the ship. But you can't come back to the same world you left. Earth will have moved on without you. And here's a subtle detail that makes the universe even stranger. Even though length contraction is real, you would not simply see objects squashed. Vision in relativity is tricky. Suppose we cross near a planet that's rushing toward us. The planet is contracted along the direction of motion. But because light takes time to travel, the light from the back of that planet reaches us later than the light from the front. That delay changes the image we receive. So instead of appearing flattened like a pancake, the planet appears rotated. That's the Terrell-Penrose effect again, now linked to physical contraction and light travel delays. A person watching our ship at near light speed would also not see it as purely shortened. They would see it as strangely rotated because the photons arriving from different parts of the ship were emitted at different times. As we keep accelerating, our field of view continues to compress. The front becomes brighter and tighter, while the rear darkens until it's nearly black. It's tempting to ask, if we accelerate forever, will we eventually reach the speed of light? What would we see at that exact moment? But relativity gives its most important answer. We will never reach it. No matter how long we accelerate, light always escapes from us at the same speed. From Earth, observers would see our speed approach the speed of light more and more closely. But from our own perspective, we're always at rest, and light continues to move away at light speed. That limit cannot be crossed. The best we can do is chase it forever. And as we do, the universe ahead squeezes into an intensely bright point, surrounded by a sky that becomes completely black. At that point, almost all the light we can ever see is concentrated in front of us, and almost all the universe behind us becomes unreachable. The aberration and Doppler effects, which started as curious distortions, now become extreme. Light from every direction gets pushed into a narrow cone ahead, as if the whole cosmos is being funneled into a single, blinding spotlight. Meanwhile, light from behind cannot catch up. In our frame, those photons are chasing us but never arrive, so the rear of the sky turns into permanent darkness. Visually, it would feel like the universe is collapsing forward, not because space is truly folding, but because at near light speed, the directions from which photons can reach us shrink dramatically. And because of length contraction, the universe itself appears compressed in the direction we're traveling, like a thin sheet we slice through. From Earth, we would appear to be moving at almost the speed of light, but from inside the ship, our trip through space feels unbelievably fast, even close to instantaneous. So, the conclusion so far is clear. Nothing with mass can ever travel faster than light through space. We can get closer and closer, but we can't reach it, and we certainly can't exceed it. Yet science fiction keeps tempting us with a loophole. What if we don't move through space faster than light? What if we move space itself? Here is where general relativity enters the story. Special relativity sets the speed limit for objects moving within spacetime. General relativity, however, teaches that spacetime is not fixed. It is dynamic. It can stretch, curve, and evolve. And this means there is a theoretical way to bypass the rule without breaking it: a warp drive. A warp drive wouldn't be about pushing a ship through space faster than light. It would be about creating a bubble of spacetime around the ship and moving that bubble. The ship inside would remain locally at rest. It wouldn't break the speed limit because within the bubble, the ship isn't outrunning light. Instead, the space in front of the bubble would contract, and the space behind it would expand, effectively carrying the ship forward on a moving wave of spacetime. This idea sounds impossible, and with our current understanding, it likely is. Creating such a bubble would require enormous amounts of negative mass or negative energy, something like exotic matter, which has never been observed in a usable form. Still, the mathematics of general relativity allows us to model it, and that means we can ask the same question again. If a warp drive existed, what would we see? From the outside, the warp bubble would be bizarre. It would look like the ship appears out of nowhere because the curvature of spacetime bends the paths of light rays around it. The bubble acts like a moving lens, splitting what we see. Some rays are dragged forward with the bubble, others are pushed backward. And because the warp bubble moves faster than the light outside it, the timing of what reaches an observer becomes strange. Light ahead of the bubble hasn't had time to arrive yet, while light from behind can pile up. In effect, the ship would seem to distort the universe around it as it travels, leaving warped images and shifting brightness in its wake. Inside the warp bubble, the view becomes even stranger. Ahead of the ship, the sky would appear contracted, but much of it would dim or even vanish because light from certain directions would never be able to catch up to the bubble. Behind the ship, the opposite would occur. Light could accumulate, making the rear region appear intensely bright. The universe would not look normal in any direction. In fact, a whole patch of the sky would simply disappear. There would be a cone-shaped region that remains permanently invisible because photons from that part of space are too slow to ever enter the warp bubble. So, even in the fantasy of faster-than-light travel, the cosmos doesn't become simple. It becomes more distorted, more asymmetric, and more unsettling. And that's the real lesson hidden beneath all of this. The closer you get to light speed, the more reality refuses to match intuition. Space bends, time stretches, distances shrink, and vision itself becomes warped by the simple fact that light takes time to reach you. Relativity isn't just a set of equations, it's the universe telling us that speed changes what it means to see, to travel, and even to exist.